in video number 7, we're going to talk a little bit more about elimination reactions. It turns out that with elimination reactions, we have multiple choices. We have many, many different possible products. With substitution reactions, that's not the case. So in a substitution reaction, if you have a back side, here's my leaving group, this is the site that's going to get attacked. And whatever is right here, this is going to leave, and the nucleophile is going to replace that position. We also know that if this is a chiral center, for instance, if this was wedged, the final product will have the nucleophile, which is in a dash, because the nucleophile is going to be opposite to wherever the leaving group was. That's one product, only one product. I go from this is a 1, 2, 3, this is an R to an S configuration. And that gives me one product because I'm attacking this one position. And that's why a substitution reaction is only going to give you one product. There is the case in which a substitution can give you two products. The case when a substitution can give you two products occurs when the reaction itself is an SN1 reaction. So let's see here. I have this substrate. This substrate is tertiary, and if I want to do a substitution reaction with this tertiary compound, I have to wait until this bond breaks. When that bond breaks, I'm going to create something that looks like this, and I have a carbocation right there at the middle. Now, when the nucleophile, when the nucleophile adds, my nucleophile could add from this direction, or my nucleophile could add from this direction. Why is it that the nucleophile can add from two different directions? Because it doesn't require a back side anymore. A carbocation is trigonal planar. Something that is trigonal planar is flat. When something is flat, a nucleophile can come from this direction and attack it, or the nucleophile can come from this direction and attack it, which means that the product of this reaction is going to be a mixture of R and S. Since this is a chiral site, I am going to end up with a compound that has a dash and a nucleophile, and I'm also going to end up with a compound which has a wedge as the nucleophile. The question is which one of those two predominates, and the answer is neither one of them. It's an absolute 50-50. When you have a 50-50 mixture of enantiomers, the R, the S enantiomers, when you have a 50-50 mixture of that, we call it a racemate. A racemate, or a racemic mixture, is a mixture of both the R and the S. That is a result of a nucleophile attacking a carbocation. When a nucleophile attacks a carbocation, if it makes a chiral center, 99% of the times it doesn't make a chiral center. But if it makes a chiral center, it will make an equal mixture of R and S, and you will have two products instead of one product. That's the most complicated that a substitution reaction can get. You can either get the opposite chirality if you do an SN2 reaction, or you can get a mixture of 50-50 racemate when you do an SN1 reaction. Those are your only two options, but you're only getting those products. Now let's take a look at the complication with an elimination reaction. An elimination reaction, on the other hand, has the possibility for multiple products. Why does it have the possibility for multiple products? Because in an elimination reaction, that which is being attacked is not the stereogenic center. It's not the alpha position. The position that is being attacked is the beta position. That is the hydrogens that are one away from that site where the leaving group is located. So if I look at this structure in particular, I have a hydrogen right here, which is not drawn, but I know is there. And that hydrogen is a beta hydrogen. And then if I go over here, one away, see this is one away. If I go over here, one away, there are 3 hydrogens over here, and they are all beta hydrogens. And then finally, if I look over here, there are 2 hydrogens, and they are also beta hydrogens. So if I have a base, and a base is going to come and remove one of these hydrogens, which hydrogen is it going to choose? Now, all of the hydrogens have pretty much the same partial positive charge. So the base is not going to know the difference between any of those hydrogens. We could go just by the numbers. This is 3, this is 2, this is 1. So the chances are that we could produce, and I'm going to do over here, we could produce this compound. Remember that you're removing a hydrogen, but you're also removing the leaving group, and so we're going to create a double bond right here. We're still going to have the 2 orange hydrogens over here and the 1 blue hydrogen over here. That we still have 2 green hydrogens over here, but we're minus 1 green hydrogen. The other possibility in this reaction is for the base to come and remove the blue hydrogen. If I remove the blue hydrogen, I would have a blue double bond between the carbons where that hydrogen was located. I will also have the leaving group somewhere, and if I look at everything else is still the same. I still have 3 green hydrogens over here. I still have 2 orange hydrogens. But this double bond and this double bond are completely different. These are completely different structures. They have different connectivity. They are isomers because they have the same molecular formula. But the only thing that they have in common is that they are constitutional isomers. This is not a matter of RNS. This is a matter of the double bond being located in a completely different direction. So we're not actually even done because the base also has a choice of being able to pull off one of the orange hydrogens. If the base pulled off one of the orange hydrogens, I would end up with a structure that now had an orange double bond in that position. And this position right here is different than the double bond here and the double bond here. So I now have created 3 different compounds. And yet there's actually more, because in this case, it doesn't matter. And in this case, it doesn't matter because they're exactly the same. But in this case, with the hydrogen protons, if I removed the other hydrogen proton, I would actually get a different product. What product would I get? If I removed that hydrogen, I would get an orange double bond right here. But notice that this compound and this compound are not the same compound. The double bond is in the same location. Absolutely. It's in the same location. It's between this carbon and this carbon. This carbon, this carbon, this carbon, this carbon. But the compound is not the same. Why not? Remember the cis and trans relationship? All of a sudden it's going to come back and haunt us. So we're going to have an E and a Z. In this case, this has priority and that has priority, so they're on opposite sides of each other. So that is an E double bond. And in this case, this and this are the major ones, so that's a Z double bond. So without too many other possibilities, all of a sudden an elimination reaction can give me many, many products, because it all depends on the substrate and how many beta hydrogens there are. In a substitution, you get 1 product, maybe 2 products. But in an elimination, you get many, many different possible products. So again, the question is, which one of these products is going to be the major product? And which one of these is going to be the minor products? Well, we're going to have many different minor products, and the truth of the matter is that until we look at this specific reaction, the energetics of each one of these different compounds, it's hard to determine the order of highest or most stable to the least stable compound. But we can use stability of the compound to determine which one is the most stable, and probably can also dictate which one is the least stable. How do we do that? Well, in a previous video, we showed you that the stability of a double bond was completely dependent on how many substituents it had. Meaning, a double bond that was tetrasubstituted was more stable than something that was trisubstituted. That was more stable than something that was di. That was more stable than something that was cis. That was more stable than something that was terminal, and was more stable than something that only had a mono-substituted compound. So based upon the stabilities of double bonds, I can choose which one of these compounds is going to be the major compound because it's going to be the one with lowest in energy. It's going to be the one that is more substituted. So if I look at this one, this is tri-substituted. If I look at this one, this is tri-substituted. If I look at this one, 1, 2, 3, 4, this is tetra-substituted. And this is, hydrogens are not part of the substitution, but here are 2 carbons, so this is di-substituted. When I look at all the possible compounds that I have, I'm going to find out that this compound right here is tetrasubstituted, so it's going to be lowest in energy, which is going to make it our major product. Then I look for the one that has the least substitution, and that's going to be the one that is di-substituted, and I'm going to be able to say that this is the least, or the minor product. Notice that these are minor as well. I will also produce these products. Remember that when it comes to that beta hydrogens, they're all considered the same. None of them have more energy or less energy than any other. The base doesn't care whether it takes a green, a orange, or a blue hydrogen. It's the same to it. It doesn't care which one it has. So you're going to produce the product that gives you that which is the most stable product. And the more stable product is going to be the one that is the most substituted. Because stability of double bonds and which double bond you produce becomes super important, there's actually names for these 2 different compounds. The one that produces the double bond in a more substituted position, the one that is the most stable, is known as the Zaitsev. Yeah, I know. Germans were really big in those days in organic chemistry. They since have slowed down, but Germans, Russians, and Americans were pretty much the forefront of all of organic chemistry. Now we're finding more organic chemistry happening in Japan and even in China as well. But a lot of our named reactions are going to have Russian names. The other compound, however, the one that gives the double bond and the less substituted, is known as a Hofmann double bond. Hofmann is a German name. So we have a German and we have a Russian. And the idea is that the more substituted the double bond is, you're going to get a Zaitsev product, or the more stable product, or a Hofmann product, or the less stable product. It turns out that we can determine which one of these 2 is going to be the major product. We always know that the Zaitsev is the one that is the most stable or the more substituted, and the Hofmann is the one that is the least stable. But we have discovered ways to choose one of them over the other one, meaning that we can make the less substituted double bond the major product if we do it in a specific way. And that's what I'm going to show you on the very next video.